Okay, great. So, hello everyone. Hope you are well. And let's start our second semester, second part of the AI Club. So today we will discuss the convolutional neural networks. We already have discussed a little bit different architectures of neural networks, but now we will dive into details of convolutional neural networks, which usually shine at working with images in computer vision problems. So, but firstly, let's recall the previous lecture. There we talked about attention is all you need paper, so the seminal paper in the field in deep learning. Then we dive into details and discussed the math trick in self-attention mechanism. And in the end of the lecture, we discussed layer normalization dropout, and during the whole lecture, we actually built the GPT-2 transformer neural network for working with, for generating text data letter by letter, so in character level. And today we are going further, and this is the first image of you see two old folks, and apparently they are something like scientists, researchers. You see a lot of devices around them, and the question is, so who they are? Yeah, actually. Of course, this is very hard questions. I'm sure you you don't know, but these folks are Hubel and Weissel. And why I am showing you them? So actually, they are Nobel Prize winners in physiology or medicine. There is such nomination in Nobel Prizes. So physiology or medicine. And yeah, it happened in 1981. So what did they do in previous time? Actually, they conducted very interesting experiment with cats, with you see animals. They put the electrode into the brain of cat. So you see here the electrical signal from brain goes through with this electrode to the devices, and then this way they could measure the signal from cat's brain according to the different visual stimulus. So you see cat looks at the some screen with actually simple black stripes on the screen, and the signal from the brain, from the certain part of brain, shows us that actually the response in this certain part of brain is very similar to some certain peak, which represent, here you see the orientation is 0 degrees, so it means horizontal line. So certain part of the brain activated, then cat looks at the horizontal stripe, and doesn't activate it if cat doesn't see this stripe. So for each orientation there is some different part of brains which is activated. So this was the very important result, not only for understanding of humans' vision, but also in the future for modeling it, and not understanding in general, but simulating the human vision in computer fields. So in computer vision, actually we borrow this idea, and we discuss how, but now I want you to understand this very simple principle. So if we can distinguish between black and white, then we can perform the next level operation. So how to understand the orientation of black line here. And we can build, if we can distinguish the orientation of line, then we can build the angle from two lines. Yeah, this is clear. So this is some hierarchical structure of actually of vision process. So the next step, if we can detect angle, then we can build triangle as three angles combined with each other. And here you see very simple detector of triangles. And actually we want to implement this simple idea with computer, with some model to be able to detect, for example, triangles. And of course then the next step is getting images, for example, images of cat, yeah, so the pictures of cat, how to build it if we can detect triangles, for example, and circles. Of course, it's not very hard, so let me draw some picture of cat, yeah, so you see this is two almost triangles, then one circle, then another two circles, and then something else. And this is the picture of cat. So if we can detect all the parts and then combine these in the final level of our model, then we've done with the task, and we will detect, for example, the picture of cat. Okay, let's go on. Let's go on to the first step in computer modeling. So actually, something like convolutional neural network already appeared in 1980. And yeah, this is history, but this is important. The life of ideas. Yeah, so the Fukushima Japanese scientist used convolutions and activations in his model of analyzing images, actually. So you see here, square is image, and then we translate it to some vector of numbers. But here, so at that time, there was no any gradient descent optimization or supervised learning, so there were no any answers. But still, the idea is here, and then if we nowadays we understand that if we add our deep learning optimization schemes to this model, then we probably will get very good model for images. And that's true, actually. So the first success came in 1998 with seminal work of Jan LeCun. He is alive. You can look at his video nowadays. The researcher from France, and now he is working in Meta company, and other authors are well-known scientists too. So Bengro, and they came up with first really great neural network for classifying images. So here you see some scheme. We will dive into all the details and discuss what is going on here. But you see, the scheme is not very difficult. It is similar as image to the Fukushima model. And actually here we have layer by layer construction, which represent image from the input with some vector of 10 numbers. So here we have output with size 10 because we want to predict digits. So for example, digits from 0 to 9 and the output has 10 classes. So each number here is raw score prediction for certain class, as we discussed earlier for any classification model. So here you see the output, and then we will go through all other layers, which will be very similar to the idea of hierarchical recognition of parts of the images and then combining them to the actual image. And this neural network is called linear architecture, so because of the first offer. The Kuhn is offer of linear architecture. Then it was really huge breakthrough in 2012, and this architecture, it is called AlexNet. Again, for the sake of the first author, Alex Krzyzewski, but you see the second author is Ilya Sutskever. He is co-founder of OpenAI, and now he moves to other company, and he co-founder of other company in the field of LLMs. But this is very strong result from the time, and the Hinton is also very well-known scientist in this field. Again, you can look at his video, and he is alive too. But this is AlexNet convolutional neural network architecture, and actually it was the winner of the ImageNet contest for the 2012 year. So the ImageNet contest is the classification competition, so to classify a lot of images, millions of images, with respect to 1,000 classes. So you see the output of this net is vector with 1,000 raw scores, and each score represents some certain class of the image. So let's go on. And again, here this is only convolutional layers. We will discuss what does it mean. But the AlexNet is not very different from LeNet, but of course there are some interesting steps, and we discuss all the details. But let's start with reminder. Yeah. So what is linear model? Let me recall you that in general in machine learning we always have the set of objects X, and each object usually represented as a set of features. So for X object we usually have X1, X2 and so on, Xn numerical features for this object. And using these features we can build different models, different machine learning models. For example, one of the most simple models is linear one. So if we multiply all the numerical features to some weights, and then this is dot product of two vectors, yeah. And if we also add some bias term, this is also parameter of the model, then this result is already raw score of some prediction. So we want to solve some task, for example, classification task. And then we need to apply activation function for this raw score, and so the activation function can be sine of the result, or sigmoid, or even this is ReLU activation function, so simply maximum or zero from Z score. And this is, so if we, for example, apply sigmoid function to our raw score, then the result will be from 0 to 1, and it can represent the probability of certain class. For binary classification problem, it simply be the probability of first class, for example. And that's it. So the linear model is quite simple, and we can represent this model as one neuron. So this circle means that it has all the weights, W1, W2, and so on to Wn, and we multiply weights to the to the features from the input, and the result is our output y. Yeah. For example, it could be probability of first class. Okay, so now we are able to stack neurons. So if we combine neurons with each other, then we will get some linear layer. Yes, so simply m linear neurons. Then we can stack layers together one by one, and then we will build some neural network. So the model consists of neurons, of different neurons. So as children build some constructions from Lego blocks, we build models from neurons, from different neurons, and we create layers of our linear models actually with some activation function. And here is again the picture of convolutional neural network. So each layer here makes sense. We will discuss, but again, from the high level picture, the input is some image, then goes convolution layer, then pooling, then again convolution, pooling, and here is fully connected layer. It means actually linear layers consisted of, for example, 512 neurons and so on. So let's go deep and discuss each layer one by one. And of course, we will start with convolution. What does it mean? What is it? So the convolution in neural networks is simply sum of products for all the elements in your feature detector, or in your filter, or in your kernel. They are all synonyms. So you have some metrics, for example, 3 by 3, yeah, and this matrix has some weights. They don't need to be either 0 or 1, but it is also possible. Usually weights are numbers either from 0 to 1 or from 0 to some other number, but then you simply multiply. So you put this feature detector on each part of the image, and then multiply your weights on the corresponding intensities in picture. Okay, so your, for example, grayscale image is simply matrix of different numbers. And then you get the first answer. So this is your new image, which is called feature map. And from the input image here, you go with your feature detector as sliding window, and step by step, you will fill in all the values in your feature map. So the result, the output, will be the same form as input image. If you but here you see we need to cut boarding cells, because our feature detector has form 3 by 3, and of course we need to start. So the center of our feature detector should goes in the inner cells of the image. That's why we cut border cells, and this is our result with new numbers. And you see here, so this is very important, we built the directions x and y into the model. So by convolutional layer, we don't use all the weights with the size of images. It is possible, but it will be a linear layer. No, here we use only 9, for example, 9 weights instead of, you see, the size of image. And actually, we can get the same accuracy with this simple convolution layer with 9 weights only. This is, and we built into the model the x and y, and of course it is important because all the images are two-dimensional, and we want to build it physically in our model. So the horizontal and vertical shifts are not so important. Of course, they're important, but feature detector will give us different values depending on the coordinates of our window. And that's it. This is convolutional layer. So we train 9 weights inside the feature detector. So yeah, why is it called convolution? It's actually a term from mathematics, because in mathematics there is convolution function, but it is slightly different from this definition. You can convolve one function with another, and they used heavily in signal theory, in theory of signal processing. But now we simply use this term for some new layer of neural network. And yeah, it is important to note that, of course, the implementation of convolution actually effectively multiplies matrix by vector. So by one step, yeah. So we don't need to go step by step with this sliding window. We simply get all the results in one operation. And you can, if you are interested in, you can read the article. But for now, the only thing we need to understand is how convolution works. So this is another example with three-dimensional kernel. If the input image is colored, so it has 3 channels, yeah, red channel, green, and blue RGB image. Then, of course, we need to use here you see 27 weights. So the first 9 for red channel, the second 9 for green channel, and then the last 9 for blue channel. Then we take all these weights and multiply these 27 numbers on the intensities from the image. Again, here the image is 3-dimensional tensor, yeah, because we have three channels, and the center of this cell gives us one result. So you see here we go from left to right, from up to bottom, and we fill step by step. We fill the output feature map, adding bias, another parameter. So in total here we have 28 parameters, so 27 weights plus 1 bias. And that's it. So we can transform the input colored image to 2-dimensional feature map as output. And then, of course, we can perform another convolutional layer if we want to do it. And that's it. So the convolutional layer is quite simple. It incorporates into the model the horizontal and vertical directions, and it uses very few weights comparing with the linear layer and fully connected layers. And then some other technical details. So if we don't use any so-called padding or strides, it means we go step by step, so one by one. If we want to use padding or strides, then we simply go, for example, 2 cells each step. Yes, so you see here, padding with value 2 gives us smaller feature map as output. So yes, stride is our step, the size of step, and padding is the amount of cells which we add to the input image. So if we want to add, usually it is zero padding. If you want to add zeros, then we use padding 1 or 2 or more if it is reasonable. So that's it. There is the last parameter, which is called dilation, And you see here we can go not with consequences cells, but we can use this larger map to be able to look at the wider range of images and to get the same, almost the same feature map with larger image. And some questions here, some mathematical question, how to calculate the size of the output. If you know the filter size, for example, 3, the size of input image, which is 28, for example, again. And if you know stride, and let's say it is 1 and padding is 0, then of course this is really easy exercise. You simply look at the sizes of input and future output, and you will very fast understand that we need to subtract filter size from the input size, then add 2 times padding, because this is 2-dimensional image, and we need to cut so we need to cut border cells, but here is padding which prevents cutting border cells, because we add some virtual board to the image. And then we simply divide all the stride, and this is the result. So adds 1, and if the size of input is 28, and with all these parameters, the size of output, feature map of output will be 26. So two ones smaller than the input size. Okay, so, and let's go on. So it was the convolutional layer. The next one is pooling layer, and maybe it is the most simple layer, except maybe activation function. So in pooling layer, what is going on? You simply divide your image or feature map into parts, again with sliding window. Here you see the window with size 2 by 2, and then you simply select maximum from these, or all these cells. For example, here red maximum is 6, then green maximum is 8, and you put it instead of all the window. Then here is 3 and 4. So this is your result. So with max pooling 2 by 2 and stride 2, we will get twice smaller image as output. And that's it. So you simply decrease the dimension of your feature map. Sometimes, so there was average pooling with max pooling, but nowadays almost everybody uses only max pooling, and that's enough. It works quite good. Okay, and actually that's almost it. So again, of course, we need to insert some activation functions inside our neural layer. So sometimes it was, maybe you remember, the sigmoid function, which is 1 divided over 1 plus exponent of minus z, or it can be 10h function as activation, or it may be ReLU function, so the maximum between z and 0, yeah, and maybe some other approximations of threshold functions. So yeah, and of course, so we need to carefully choose the activation function, but for now we will analyze only previous good models, and we will discuss how they construct. So yeah, the question is not so easy. What are the disadvantages of the logistic sigmoid? And maybe you remember, so the main disadvantage of logistic sigmoid is the problem of vanishing gradient. So if you consider the value of sigmoid in 0.3, 4, 5, and so on, so the value will be almost constant, and the derivative of the logistic sigmoid will be almost zero. And this is the problem for gradient descent method of optimization. So actually we don't want to be our gradients close to zero. That's why we usually get rid of these activation function and use, for example, ReLU instead of sigmoid and even 10H. Okay, so let's go on. This is the image of history of ImageNet competition. So ImageNet dataset has a lot of images, and the task is to classify them with least possible error. So here you see the classification top 5 error. What does it mean? If the predicted answer of your model lies in top 5, then you get 1, so you get correct answer. If not, then you got 0, and then you calculated the top 5 accuracy of classification for your model. And you see in 2010, so these are first attempts of neural networks, shallow networks, and you see the error is high, relatively high. Yeah, so it is 28% and so on. Then you see here AlexNet, so the winner of 2012 year, and it already has 8 layers. Then some modification with 8 layers. Then goes the last linear neural network model with 90 layers already, and you see the error is decreasing with time each year. And then in 2015, so people could be able to use more than 100 layers, and the error here is already less than human error in the same classification task. So this is the moment where people almost solve the ImageNet classification task, and then we switch to top 1 error, and nowadays even top 1 error is close to 100% with modern neural networks. And we want to dive into this history neural network firstly, and this is AlexNet and what is inside this architecture. So again, the same picture, but now let's discuss it in details. So firstly, look at the input. You see, input is a 3-dimensional image. It means it has red, green, blue channels. That's why there is 3 here. And the size of image is 224. So you see 224 here. Then, so it has 2 parts. So the upper parts and the down part. They are the same. And let's discuss only the bottom part of this model. So you see 11 by 11 filter size. So this is convolutional layer with filter of size 11, and we simply perform all this convolutional layer, and the size of resulting feature map is 55. So you see here 55 by 55, and you perform 48 such filters. So it's not one convolutional layer, it's not one filter. It is 48 new channels. It means we use 48 filter maps, different filter maps, and each filter map has 11 by 11 weights inside. So we train all these weights. And the result, this is our output. Yeah. So the feature map, three-dimensional tensor with 55 by 55 by 48 dimensions. Yeah, and then we perform the same. So of course, inside each convolutional layer there is activation function, but then we perform again convolutional layer with, so here you see 5 by 5 filter, and the depth of this filter is 48. So each application of this filter gives us one number, and the one filter gives us one feature map for this block. Okay, so the size of new feature map will be 27 by 27. Let me say, yeah, so after convolution, why we here we have this decrease of size? Because firstly we apply convolution and then we apply max pooling with size 2 and with stride 2. So that's why our dimension of image decrease actually 4 times. Yes, so we divided 200 to 4 and gets 55 as size. And then again we decrease 55 to 27, so we divided 2 because there is max pooling after convolution. Okay. Then, so the next step after again we perform convolution and max pooling here. So 27 becomes 13 here, and this number again is amount of all the channels. It means we use this amount of filters on previous convolution layer. Okay, then we repeat the 3 by 3 filter map 2 times without max pooling, and then goes last max pooling, so 13 by 13 transform to 6 by 6, and then we simply flat all the features from the feature map from this three-dimensional tensor to one-dimensional vector. So simply flat it line by line. Then goes dense, means linear layers, so fully connected layers. And so we here two dense layers means some actually classification model at the top of the neural network. And then the last linear transformation gives us 1000 classes. Again, the final dense layer. So this classes, this vector consists of raw scores for 1000 classes. And that's it. So you see, we perform transformation from the two-dimensional image with 3 channels to one-dimensional vector with 2048 features inside. And then we perform actually linear classification model to this feature vector. So this is what is going on inside this architecture. So for us, it's not very difficult to implement this architecture in PyTorch, for example, and to repeat the results of 2012 year. And the top 5 final accuracy of this model is really good. So the error decreases almost 2 times, you see, so 1.5 times. And the activation function was very low. Then they add L2 regularization term with constant with this constant, and there was some data augmentation, so they changed images to enlarge the data set to train the neural network. Then there was dropout layer, but actually we can get rid of it and put dropout to 0. Then we have discussed batch normalization previously, and we said that in NLP tasks, now in transformer models, people usually switch to layer normalization instead of batch normalization. But here in this AlexNet model, so there was batch normalization layer and the stochastic gradient descent as algorithm of optimization with 0.9 parameter. And then with some very simple scheduling. So firstly, learning rate is 0.001, and then decrease 10 times after quality stabilization on the test data. And that's it. So you really can easily implement the same AlexNet structure and check all the results either on ImageNet or on other data set. And actually you will have, so today the first assignment will be Kaggle competition to implement different convolutional neural networks. For example, you can start with LeNet, then switch to AlexNet, and then goes further to modern modifications, for example, to residual net architecture to get better and better scores. And yeah, so maybe one of the final slides for today, what is momentum method for stochastic gradient descent? So previously in classical SGD optimization, we used gradient of our model. So as velocity of changing weights. So we simply subtract gradient times the learning rate from the weights, and that was the formula of stochastic gradient descent. Now in momentum, in some simple modification momentum method, we use gradient as acceleration of the change in model weights. So you see we add new vector here v, and this is velocity. So velocity of changing of weights of model parameters. And that's it. So we firstly calculate the velocity of changing, and then we update parameters with this velocity. That's it. So the goal of this momentum method is to force model to remember previous direction of our movement to the optimum. And the momentum method sometimes is more stable and gives you better convergence to the minimum of loss function. Okay, and actually that's it for today. So we discussed the structure of convolutional layer in convolutional networks. These layers are very well suited for image processing, and we come up with this layer through analogous to biological vision mechanism, and it is really computationally efficient, very well fitted for image processing. And even today, with visual transformers, we have them, but the convolutional neural networks are alive. They are standard for computer vision tasks, for simple tasks. If you don't need, or if you don't have the huge data set for your tasks, you can train some simple modern convolutional neural network, and it will work very, very good. So you can watch to the demo of different convolutional neural networks in JavaScript. So let me show you how it looks like. For example, classification of NIST digits with convolutional neural network. So now here, looking at the layers, you can understand everything, because this is the input layer with input size 24 by 24 and the grayscale images. Yeah, then goes first convolutional layer with size of filter and amount of filters, so the number of all the filters, stride and padding you need to specify, and the activation function. Then after first convolutional layer goes the first pooling layer with size 2 and stride 2, so you decrease the size of image of feature map 2 times. Then goes second convolutional layer with different parameters, max pooling with size 3 by 3, so here you reduce the image size by 3, factor 3, and then goes the last soft max layer, because you have 10 classes in your data set, and that's it. So your model predict 10 raw scores for input image, and then you simply train these neural network with stochastic gradient descent, with other delta, for example, optimizer, batch size, and L2 coefficient for regularization. And you see how loss function is changed, and what are predictions of the input. So you see for all the layers, the pictures of activations, and then the answer for different images. Yeah, so you see the this model works very, very well. Almost everything is green. Yeah, sometimes it has errors, but now we don't see any errors. So you see 4 is 9, but the picture is similar to 9. Yeah, so for us, for strange pictures, we sometimes model sometimes has errors. That's so it's simply trained in your browser with in 2 or 3 minutes, and of course you can change different parameters, and you can change architecture of the model. And maybe the final step, let me show you our Kaggle competition for homework assignment. Yeah, that's this is it. So again, through Cognitera you can go to the join competition link, and then you need here to classify the data set of street view house numbers, slightly changed, and the task is to improve all these solutions. So this is benchmark scores for different models, and then gradually you will implement different neural networks one by one and get higher and higher score. So here you even will have quite simple baseline notebook, and you can use Google Colab for training, and this is all the description with classes to upload images, and the only part you need to change is here, so the classification model. So in baseline we write very, very simple model. It is one linear layer, yeah, so from this size of image to 10 classes, and that's it. And even this model is trained with some quality, yeah, so the accuracy is more than 21%, but of course the model is very simple, and then you add different convolutional layers and different architectures, you will get much higher accuracy in this task. Okay, and here let me show runtime. Better to, if you are able to use GPU, so either GPU from Google, or if you have Pro subscription, you will be able to select A100 GPU. It really allows you to train your neural network very fast. So yeah, that's it for today. If you have any questions, yeah, please ask. Okay, great. Then see you next week. We will write everything in our Discord channel. So yeah, thank you for your attention. Have a nice day.